7.3 is on exponential functions, which will include inverses. So it will tie right into 7.2 that we just looked at in the previous video. So this would be more typical definitions that we're used to at first. So we're going to define exponential like this: f of x equal to b to the x, where b is positive and not equal to 1. And a couple examples I'm sure you've seen before. Y equals 2 to the x, very typical one to do first. Then you look at the inverses of those, or reciprocals of those. Y equal to 1/2 to the x, or you could write that as 2 to the negative x, like that. And that, of course, has a completely different graph. Then you have like so that's the base. So we say, we say f, and then so this is base b, base 2, and then base 10 would be like 10 to the x. That's the base of it. And we know that there's a number e for the logarithm, right? For the natural log, we know there's this number e that the graph is equal to at 1. All right, so that's, anyway, I'm going to graph this first. Okay, so there's a logarithm, and then we have, hold on a second, I fixed my iPad there for a second. Then you have this graph. I'm not sure why I'm doing these now, but so this graph is y equals log base bx, and this graph is y equal to b to the x. And then if you have it negative, of course, then you go this direction, right? And then in this direction. Okay, we'll do those. We'll leave those to you to graph. I'm sure you've seen those. We have y equal to e to the x. I was starting there, but I went ahead and graphed stuff. So e, we already know, is approximately 2.718281828. Transcendental, non-repeating, irrational number. Okay. So if we're defining f of x, a different function now. So suppose f of x, or call it g of x, whatever, is ln x. We know that definition is the integral 1 to x, 1 over t dt. Okay, so we actually know what that is, and we defined e based on the property that you get 1 when you add that up. So basically, f inverse then is e to the x, or vice versa. It doesn't really matter. So when they're they're inverses. So we know it's 1-to-1. Inverse exists. That's that kind of thing. So we know f composed with f inverse of x is equal to f of f inverse of x. So that would be written as ln e to the x, which we know equals x. And then the other way around, f inverse composed with f of x is equal to f inverse of f of x. So that would be e raised to the ln x, which we know is x. So this is by the definition of inverses, or is the definition of inverses. So now let's look at the derivative of e to the x. And how would you show that? So check this out. The derivative of e to the x. That's just my title here. Okay, so let's look at ln. We know ln e to the x is equal to x, since they're inverses. Okay, so since inverses. Now let's differentiate both sides. Now recall that when you have so d dx ln e to the x equal to d dx of x, we know the right hand side will be 1. And we also remember that d, like ddw, I forgot the dw part, ddw of ln w is 1 over w. Okay, so this left-hand side, d dx of this is going to be 1 over e to the x. So you get 1 over e to the x, and then that's the derivative of ln x. Then it's times the derivative d dx of e to the x, right? So it would be times what's inside prime. We don't know what that is. We're figuring it out. But that equals 1. Okay, so then just solve. Multiply by e to the x. When you do that, multiply by e to the x, that's gone, and it tells you what the derivative is. So then you get d dx e to the x is equal to e to the x. So the derivative of e to the x is e to the x. Okay, so don't ever forget that. You need to know that forever. Okay, so derivative of e to the x is e to the x. So it's the only function that whose derivative is itself. Okay, so the derivative of e to the x is e to the x. So then you have chain rule, of course. So one of the properties you can look at is if you have d dx of e to the u, where u is a function of x, then you just write e to the u times the derivative of the top, times u prime. So if the derivative of e to the x is e to the x, what do you know about the integral? So that means that the integral of e to the x dx must be e to the x. And then you do have an arbitrary constant, of course, because if you go the other way around, you would take a derivative of c and get 0. And then you have, you could replace that with u. So, I mean, basically, same thing, e to the u du, sometimes you'll see it written, is equal to e to the u plus c. All right. So very important definition and concept, actually, because of that. Let's look at an example. Right here. Okay, so let's look at this example. So evaluate this. So evaluate the integral of x e to the x squared dx. So let's just do it's use substitution. So if u is that, you get a du, which gives you the x dx, plus an integration constant. So if we let u equal x squared, then du is 2x dx. Or let's write it as du over 2 is equal to x dx. So we substitute all of the x dx right here, and here's your x dx. So that is your du over 2, and do your substitution now. So that's equal to the integral of e to the u times 1/2 du. So integral of e is just e. So you get 1/2 e to the u plus c. And then substitute back 1/2 e to the x squared plus c. So it's really important that we had this x right here, because if you don't, then it isn't there isn't an explicit form for the antiderivative. One of the classic ones, I'm just going to show you this real quick, that you can look at is the bell curve. So if you have this integral, negative infinity to infinity, and you write down e to the negative x squared dx, there is no explicit form for the for e to the negative x. You don't have that x sitting here to get rid of that dx. But that is very well known. That has been studied forever. Well, not forever, but a lot. And what that is that's this graph. That's the bell curve graph. And the area, depending on values and stuff, you get area under the curve. So area under that curve is what you get. And it adds up nicely to 1, and if you have the right constants and stuff. Oops, I didn't mean to do that. So, but without that extra factor here, this does not have an explicit solution. I mean, you can evaluate it with infinite sequences and series and things like that and get as close to an approximation as you want. But it does not have a form to evaluate. Check that out. Okay, moving on. Let's look at another example. So let's evaluate, what's this one? It's e to the negative 1 over x squared over x cubed dx. Okay, so try that one. And then we'll go on and do it. Okay, then let u equal negative x to the negative 2. So then du is equal to 2x to the negative 3 dx. So then you get your du over 2 equal to 1 over x cubed dx. And there you go again. Yay, we get it. That's what you can practice. So this one's nice. So you get this will be just your du over 2 is right here. Okay, so these are straight up u substitutions. Substitute in, and once you do that, these are really always nice and easy to integrate because it's itself. So you get substitute in appropriately. Check, make sure you got this down. That's du. So you get 1/2 e to the u plus c. And then substitute in 1/2 e to the negative x to the negative 2 plus c. Okay. We will continue, it's probably a little long, but let's go ahead and continue. We look at bases other than e, how they're defined. So bases other than e. So really all I've defined so far is the natural log. It is that. That will be base e, but we haven't even defined bases of other than e yet. So let's do that first. So let's let a be greater than 0 and not equal to 1. And we're also going to assume a does not equal e. Okay, so it's not the special case. So when we write a to the x, we basically do a little trickery here. And we write that as e raised to the ln ax. It's not trickery, I just said that. Then it's, so now you bring down the x, you get e to the x ln a. So we can write any base in this form and have it just in terms of base e or in terms of e in natural log. That's what kind of makes it nice. So when you look at the derivative of that, so we look at dx of a to the x. So we have dx of a to the x. We look at this. What's the derivative of that? So that equals dx of e to the x ln a. So that is itself times the derivative of the top. So it's equal to itself, e x ln a, times this derivative, which is derivative of a constant times x, is just the constant. So that's times ln a. So we write that as a to the x ln a. So remember, this is a to the x. Right, do you see it now? Okay, so that's what we did. So this is a to the x. So this is like deriving. It's deriving how you get those formulas when you do the derivatives of these different bases. Simple example to apply that formula. ddx of, say, 5 to the x is just 5 to the x ln 5. So that's all you do. Okay, let's continue. Property. If I have dx of a to the u, that's equal to a to the u ln a times du dx. So there's your chain rule. Similarly, for integrals, a to the u du is equal to a to the u over ln a plus c. You get that extra integration constant in there, the ln a, and of course it has to come out. So these are inverses. So if you have f, right, I'm just writing down the form, f composed with g of x, and then I'll do the other way, g composed with f of x, then that's a raised to the log base ax, which is of course just x because they're inverses. And then log base a of a to the x is just x. So a lot of this, of course, you've all seen with exponentials and logarithms, but now we're defining it the calculus way. It's really the better way so that everything matches when we go forward. Last thing we'll do, I'll do it now, it will show and derive the change of base formula, and we'll do another example. Well, no, we'll just show you change of base formula. Okay, so change of base. Formula. which you would have seen, I'm sure. You have log base AX is ln x over ln A, or you can write it as log base bx over log base b of A. I messed it up. Log base b of A. What did I not show you? Oh, if you look at the derivative dx of log base A of u, then you could just change it into a different base, really. I mean, you really can just say that that's just dx of ln u over ln A. So you'd get 1 over ln A times 1 over u times u prime. You would do the chain rule. Last example, let's do the integral. Integral from 1 to e. Something special going on here. Oh, I remember this one. This one looks all weird, but it works out nice. Check it out. 2 ln 10 log base 10x over x. What? Okay, well, if I recall, it works out real cool, like real nice. Oh, you apply the change of base. That's right. So check this out. You get the integral from 1 to e. So we're going to do the change of base on this to simplify this thing. So you get 2 ln 10, that's over x, and then that becomes ln x over ln 10 if you do change of base. So those are gone. And you're left with, what? We're left with 1 to e, definite integral, ln x over x dx. Okay, so then, not necessarily obvious, I guess, right here. So let's do a u substitution. So if you let u equal ln x, then du is 1 over x dx. Now, does it look clear to you? So we just pick u to be that, and then you get the 1 over x, so you get that as your integral. And so that works out pretty nice then. You get 2, factor out 2 finally, 1 to e of u du. That's just 1/2 u squared, so the half's gone. So that's just u squared. And then we're going to evaluate that from, it's actually x equals 1 to x equals e. So let's change back so we have the same variable. That's why I put that in there. So it's ln x quantity squared, and then now we can just say from 1 to e. And so you get ln e squared minus ln 1 squared, and that equals, I'll do it here, that equals 1 minus 0, which is equal to 1. So all this mess here, that's why I like this one. Check this out. All this mess here simplifies to 1. Pretty cool, huh? I like that. It's a good one. Okay, that's it for that section. Next, we don't do 7.4. Take a look at it, some good stuff in there if you're moving on, especially to differential equations. But we will go on to 7.5 on L'Hopital's rule. something they always like to teach you early on, but you really can't do it until you get to this level. So we'll take a look at that next.